Hello everyone! My name is Raluca Posteuca and I am a PhD student in the COSIC group at KU Leuven. I am very excited to be able to present our work today at SCN 2020. My presentation is entitled Generalized Matsui Algorithm 1 with application for the full DES. This is a joint work with my colleagues Tomer Ashur, Danilo Šijačić and Stef. The outline of my presentation is as follows. In the introduction, I will present the baselines of linear cryptanalysis, followed by the related work and our main contributions. Afterwards, I will shortly present the DES cipher. In the third part, I will introduce the notions of poisonous rounds and of a strictly zero correlation linear approximation. Here, I will describe the approach that we took in order to obtain a poisonous trail for the full DES, together with the manner in which we use this property in designing a key recovery attack. The fourth section is reserved to our experimental verifications, while the last part will conclude the presentation. Linear cryptanalysis is one of the most powerful techniques used in the security evaluation of a block cipher. This technique was introduced in early 1990s by Mitsuru Matsui, who also applied the technique to the DES cipher. In the last decades, linear cryptanalysis was intensively studied, formalized, and extended in different manners. The main idea of this technique is to find the linear approximation between a set of plaintext bits, ciphertext bits, and key bits that holds with probability different than half. For simplicity, we associate to each linear approximation a mask vector uv. The linear approximation will hold if the relation presented on the slide also holds. Note that the dot represents the inner product. The quality of a linear approximation, often measured by its correlation or its bias, is one of the open problems nowadays in linear cryptanalysis. This quantity is directly related to the success probability and the data complexity of an attack based on linear cryptanalysis. In this presentation, we use the correlation to estimate the quality of a linear approximation, where the correlation is computed by multiplying the probability by 2 and subtracting 1. When the techniques of linear cryptanalysis are applied for iterated ciphers, the main approach is to sequentially linearize each round and connect the resulted linear approximations in order to obtain a linear trail. By the means of the peeling up lemma, the correlation of a linear trail is computed by multiplying the correlations of each round. In practice, it has been observed that in some cases, the theoretical correlation might be very different than the empirical one. This phenomenon was explained in 1994 by Kaisa Newberg. She noticed that there might exist more linear trails involving the same plaintexts and ciphertext bits, this being called the linear Hall effect. Since the correlation of a Hall is computed by adding together the correlations of all the underlying linear trails, different trails will interfere, influencing the correlation in a constructive or destructive manner, or even cancelling out one another. At IndoCrypt 2016, Tomer Ashur and Vincent Reime noticed that the linear Hall effect may sometimes appear at a micro level, inside a single round of the cipher. Their research and observations were applied to the Simon cipher. At Balkan CryptSec 2018, myself and Tomer proved that, under certain conditions, the F function of DES exhibits zero correlation key-dependent one-round linear halls. In our SCN paper, we extended the work presented at Balkan CryptSec by introducing a new type of attack based on linear cryptanalysis called the strictly zero correlation attack. Our new attack covers the full DES and aims at recovering the key bits by exploiting the key-dependent behavior of a linear trail. But before presenting in more details our results, let me first briefly introduce DES. The cipher was developed by IBM during the early 1970s, and it was published as an NBS, today NIST, standard in 1977. The cipher operates on 64-bit states divided into equal parts, namely L and R. The key has 64 bits, even though only 56 key bits are actually used in the encryption. DES uses the Feistel structure, based on a nonlinear function f. In one round of this, the left part of the internal state is used as an input to the f function. The output is XORed with the right part, and then the new halves are interchanged. This operation is applied 16 times since this has 16 rounds. The f function of this is composed by 4 operations. The first one is a 32 to 48-bit expansion function E. The function is applied to the 32-bit plaintext. The output of this function is then XORed with the 48-bit round key. The result is divided into 8 6-bit blocks. On each block, a different 6 to 4-bit substitution box is applied. The last operation is the application of the 32-bit permutation P. Let me now present how a linear trail through the f function of this can be obtained. Let the input mask of the trail be alpha, while the output mask is beta. K represents the key mask, tau represents the output mask of the E function, while lambda and gamma represent the input and output masks of the substitution layer. Following the rules of propagation of linear trails, the intermediate masks of the f function must satisfy the following conditions. The masks involved in the XOR operation, more precisely tau, k, and lambda, must be equal. Each pair lambda I, gamma I must be connectable through the linear approximation table of each corresponding S-box. Last but not least, beta has to be equal to P of gamma. Therefore, if we fix the input mask alpha and the output mask beta, then we also fix the intermediate mask gamma. The only mask that might take multiple values is the intermediate mask tau, which is also equal to the k and lambda masks. While introducing the linear cryptanalysis, Matsui presented the linear approximation on the full disk. His approximation uses 2 times an 8-round iterative linear trail having the correlation 2 to the power of minus 12.71. For the original attack, Matsui replaced the masks of the first and last rounds with locally better ones. The masks of each round, together with the corresponding correlation, are presented in the picture on the slide. Since the trail is iterative, we can start with any input mask and extend the trail naturally over the following 7 rounds. Note that we use such a twisted iterative linear trail in our work. In our research, we introduced a new 1-round poisonous linear trail for the f function of this. The linear approximation has the input and the output masks, the one presented on the slide. While alpha and beta have fixed values, the tau intermediate masks might take 4 different values. Each tau mask leads to a different correlation and to a different key mask. While the key mask is equal to the tau mask, we use the set notation to specify which of the round key bits are actually involved in the computation of the correlation. Note that the correlation of the 1-round hull might take 3 different values, depending on some key bits constraints. We consider a key-dependent linear approximation that might have correlation 0 to be a poisonous trail or a poisonous round. In order to compute the correlation of a many rounds linear trail, we multiply the correlation of each round's linear approximation. If one of these correlations is 0, then the final correlation will also be 0. Thus, the 1-round 0 correlation linear approximation acts as a poisonous round. We extended our 1-round linear approximation to a 2-round poisonous trail by adding 1 more round on top of the poisonous trail presented before. Note that the input mask of the first round is one of the input masks used in Matsui's trail. We therefore managed to adapt Matsui's trail by replacing the last 2 rounds with our 2-round poisonous trail. By taking into account the key schedule, the correlation of the 16-round trail based on the master key is presented on the slide. Our new trail is 1.38 times better than the original one for some keys. The correlation of our trail depends on some properties of the key bits. Therefore, our trail divides the set of master keys into 3 key classes. By observing the correlation of the linear approximation, we can gather information regarding the bits of the master key. For example, we can identify the relation between K51 and K1, or even the relation between K0 and K8. Each relation that we learn is equivalent to the recovery of one key bit of the master key, since the key space of the exhaustive search is halved. We used the distinguishing property in order to design a key recovery attack. Our attack is straightforward and implies the following steps. First, we compute the correlation of the linear approximation using 2 to the 51 plaintext ciphertext pairs. We then compare the empirical correlation to the 3 expected values, and we learn the class of the master key. Therefore, we learn the key constraints met by the master key. We computed the data complexity according to the smallest non-zero correlation, and we approximated it to 2 to the 51. In order to verify our claims, we performed a series of experimental verifications. We used software implementation for our experiments on up to 9 rounds of the trail. In each experiment, the poisonous round is the last round, so we removed rounds from the beginning of the trail. For exactly 9 rounds, we used 2 to the 38 plaintext ciphertext pairs, and we performed one experiment for each key class. As you can see in the table, the empirical correlations were very close to the expected ones, and the key classes were clearly distinguishable. We then stepped up and performed experiments on the full death. As stated before, for the attack using the 16-round poisonous trail, the data complexity is around 2 to the 51. Therefore, we used a hardware implementation based on a custom death accelerator. We performed 48 experiments for each key class, leading to a total of 144 experiments. In order to interpret our results, for each key class, we computed the base 2 logarithm of the absolute value of the mean of the empirical correlations. The results are described in the second column of the table. We also computed the success probability that a master key of each class is correctly distinguished. The success probability for each class can be observed in the last column. We went a step further in the interpretation of our results, and we plotted the distribution of the empirical correlations from the experiments, which are marked with green. We then compared them against the histograms of the respective expected values, which are marked with blue. All our experiments support the hypothesis that different key classes can indeed be distinguished. Therefore, the correlation discloses the constraints that the key fulfills. In our research, we questioned the presence of the linear Hall effect for the decipher. Our experiments show that the empirical results are indeed close enough to the theoretical values, but where the difference comes from? Can it be treated as noise, or does this exhibit the linear Hall effect and we are experiencing it? Matsui's linear attack against death was not familiar with the linear Hall effect, thus it trivially assumed that it does not exist. In fact, many subsequent works assume that either the decipher does not exhibit the linear Hall effect, or that every Hall of death contains one dominant linear trail, and therefore any other trails can be treated as noise. We proved that death exhibits indeed the linear Hall effect by identifying a second linear trail for our linear approximation. Since it can be challenging to identify another trail for the full death, we restricted our research to round-reduced versions of the cipher. We performed our search by trial and error, starting by analyzing the existence of a second linear trail for 2 rounds of death. Whenever we found a contradiction, we increased the number of rounds. We stopped at 5 rounds when we found a second trail. Since we didn't use any automatic tools for this analysis, more linear halls might exist. The correlation of the second trail is significantly smaller than our corresponding 5-round trail, therefore its contribution to the Hall's correlation can be treated as noise. In conclusion, in this work we constructed zero correlation key-dependent linear trails that cover more than a single round of death. First, we presented a 2-round linear approximation, where the last round may have correlation 0 depending on the key. We showed how to connect these 2 rounds to Matsui's trail, resulting in zero correlation key-dependent trails covering the full DES. We used the linear trail to design a key recovery attack, and we performed experimental verification of our claims on the full DES using a custom DES accelerator. Our work can be extended in different directions. For example, it will be interesting to identify other block ciphers that exhibit poisonous linear trails and revisit, if exists, the linear attacks published against them. It also remains to be investigated if and how the key recovery attack can be improved in terms of both data and time complexity, and how it affects the security of the 3-DES cipher. Future research should also consider the extension of these attacks to the case of multiple linear cryptanalysis. Thank you very much for your attention. If you have any questions, please don't hesitate to contact us.